G'day again, Year 12. Welcome back to McGrathmatics for your next lesson on nonlinear functions or curves. All right, we're starting off with a flashback question from the 2013 HSC on interest. Polly's borrowing 11 grand. She's going to repay the loan in full at the end of 2 years with a lump sum of 12 grand. So borrowing 11, paying back 12. Question is, what is the annual simple interest rate she was charged? I want you to pause the video and decide on your choice out of A, B, C, or D. All right, sweet, let's have a look. So, because we had simple interest stated in the question, we've got to be using our simple interest formula. Interest equals principal times rate times time period. Let's sub in what we know. So if we borrowed 11 and repaid 12, we've paid $1,000 in interest. That's the extra that we've paid on top. Our principal was our starting figure, rate we're trying to figure out, and number of years is 2. All right, now you can just do a bit of trial and error with these 4 values of R and see which one of them works. Or if you're not a coward, you can rearrange it and get your answer straightforward. So we can have 2 times 11 grand is 22 grand. We can then solve this equation by dividing both sides by 22,000. Casio calculator spits out 0.0455. If we times it by 100, we get a percentage. So we get 4.55%. So well done if you said B. You are spot on. You're a goddamn genius. All right, today's lesson is on sketching exponential functions. Okay, in the age of COVID, you may be more familiar with these curves because they currently map our trajectory of cases, and it's currently not looking good. Let's get into it. First example we're going to sketch the graph of y equals 2 to the power of x. Now, if we were in class, I would say, how do we sketch something if we're not completely sure what it looks like? I would point to Ruby and she would say, you've got to do a table of values. And you're absolutely right, Ruby. A table of values is correct. We're going to go from -2 up to +2. We're going to put these x values into our function and we're going to get some y values. We're going to plot them on and we're going to draw a nice pretty curve. So you should have a go now at pausing the video and putting these numbers into this equation. You're going to be doing 2 to the power of these 5 numbers. All right, hopefully you got these answers. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and then if we go this way, 2 to the -1 is a half, and 2 to the -2 is a quarter. So what's happening is as we move to the right, each time our answer is doubling, and as we move to the left, each time the answer is halving. So the next one would be 8, and then 16, and then 32, and it starts to get really big really quickly, which is called an exponential increase, which is why these are called exponential functions, because the variable x is in the exponent, which is the little power thing up here, okay? If we plot those dots onto our axis and join them up, we get this shape, which is called an exponential curve. And of course, we should be putting arrows on the end that I can't be bothered to do, but you know you should be doing it. It passes through 1 on the y-axis, and it's going to be exponentially growing up to infinity, I suppose. So there is our graph of 2 to the power of x. Let's have a go at another one. This time we're going to do 3 to the power of x, and then we're going to do +1. So if you were listening last week, you may already have an idea of what this +1 is going to do to our graph, but I won't spoil it for you. As always, if you're not 100% sure, you should do a table of values, and often HSC questions will give you a table of values to fill out, like I've done now. So we're going to put these 5 numbers once again into our equation, and we're going to get 5 answers, and we're going to see what the picture looks like. Okay, here's our answers. So we're going to do 3 to the 0 gives us 1. Anything to the power of 0 is 1. That's an important fact for you. If you add the 1, you get 2. 3 to the power of 1 gets us 3. If we add 1, we get 4. And then 3 to the power of 2 is 3 squared, gets us 9. And then we add 1 to get 10. Okay, -1 and -2 give us decimals. I'm doing a bit of rounding, which we're going to be doing a fair bit in this topic. And keep in mind that sketching curves is never going to be perfect. It's just going to be as close as we can get. Sometimes we'll have to do a bit of estimating. Sometimes we'll have to do a bit of rounding, and it's okay. All right, sometimes maths isn't perfect. If we plot these 5 points on and join up the dots, we're going to get a shape like this. So it's very similar to the last exponential, except it's a little bit steeper. So 3 to the power of x is going to be a bit steeper than 2 to the power of x. If we had, say, something like 10 to the power of x, it'd be very, very, very steep, and we wouldn't be able to graph it very easily. So I've got my 1, 4 here, and then the next point, 210, is up so high I couldn't reach it, so I'm just not gonna bother with it. I've got 0, 2, 1, 4, and then on the left-hand side, the numbers are getting really small. Last time they were approaching 0, this time they're approaching 1. Because we've got this plus 1 here, it's taken our exponential shape of y equals 3 to the x, and it's shifted the whole thing up by 1 unit. So we've got the same shape, but just shifted 1 up, and it's a little bit steeper because it's a 3 to the power rather than 2 to the power. Okay, next one's a little bit weird. So if you want, before we keep going, sorry, if you want, you can do a dotted line. That's called an asymptote. It just means it's a line that we never cross. It's something we get very, very close to, but never technically touch. As we can see, this is just going to get closer and closer and closer to 1, but never actually get there. So that blue line there is called an asymptote. Okay, for example 3, we've got a bit of a weirder one. We've got 2 lots of 0.5 to the power of x. So now the base of our power is a number less than 1. And so like I said, 3 to the power of x is going to be steeper than 2 to the power of x. So it'll be interesting to see what happens when we make the base a number that's less than 1. All right, I want you to pause the video and see if you can put these, this time we're doing 6 values into this equation and see what your 6 answers are. All right, hopefully you did that, and hopefully your numbers look pretty similar to mine. So with this one, in the last 2 examples, as we moved further to the right, the numbers were getting larger and larger, and they were doubling or tripling each time. This time, as we move from left to right, the numbers are halving. So as we move to the right across the x-axis, we're not going to have an exponential growth. We're going to have what's called an exponential decay. So our shape is turned around. Instead of getting bigger to the right, it's going to be getting bigger to the left. Okay. So if we plot these 6 points on, or the ones that we can fit at least, it's going to look something like this. So we've got -1 and 4 as this point here. -2, 8 doesn't really fit on, so we're just going to leave it for now. That's just to show you that from left to right, it's going to be doubling each time. And then as we move to the right, we've got 0, 2, we've got 1, 1, we've got 2 half, 3/4, and then again, this thing is getting smaller and smaller, smaller. It's approaching 0. It's never actually getting there. It's never crossing the x-axis. It's just getting closer to 0 as x goes on to infinity. Okay. So this is the very similar shape to the ones we just saw, except instead of an exponential growth from left to right, we've got an exponential decay from left to right. The reason for the decay is because the base of the power was a number that was less than 1. So when your base is bigger than 1, you have exponential growth. When your base is less than 1, you have exponential decay, which we're going to see some more of in the next lesson. So spoiler alert. Okay, up next, we've got similar concept, just with some bigger and scarier numbers. We've got, instead of y and x, we've got p and t. So this could be maybe profits over time. We don't really care what it is. We're just going to do some maths today. We're going to focus on the applications in the next lesson. So we've got a table of values. Our t values are going to go from 0. We're going to go in increments of 10 up to 40. And we're going to sub these 5 numbers into our equation. So we're going to make the value of t equal to 0, equal to 10, get our 5 answers. Pause it if you want to try it by yourself first, which I highly recommend. Hopefully you gave that a crack, and hopefully your numbers are looking like these. So starting at 0, we have 1.02 to the power of 0, which gets us just 1. And then we have 100 times 1 gets us 100. Okay, it's not growing super fast because the base is only slightly higher than 1. So it's a bit of a slower exponential, but it is still an exponential because the variable is in the power. Okay. So these are our numbers. So our t-axis is going to go increments of 10 up to 40, and our p-axis just needs to fit up to about 300. So I just did increments of 100 for my graph. We're going to plot the points on and line them up, and we get this bit of a weak exponential, but it is still an exponential. It's just growing slowly in the initial stages. If we zoomed out and sketched more values, you would see more of the exponential rise, but we're just looking at a section of the graph today. So there is our function graph for p is equal to 100, 1.02 to the power of t. An important feature that's going to be talked about a lot in the next lesson is that the value at the front, the thing that's multiplying, which was the 100, that is also the starting point of our graph. That's our y-axis intercept, okay? So this 100 and this 100 is not a coincidence. We're going to be seeing that a lot later on. The thing at the front is your starting point for the y-axis and where you start to grow from. All right, coolio. To finish off, we're going to have a crack at an ancient HSC question from 2004. We've got the number of bacteria in a culture grows from 100 to 114 in an hour. What is the percentage increase in the number of bacteria? So we're asking ourselves, if you grew from 100 to 114, by what percentage have you increased? Hopefully you can see that we've increased by 14, and 14 out of 100 is literally just 14%. So by going up 14 from 100, we've gone up by 14%. There's your first mark for this question. So some parts of this question are only band 3, but some parts are going to go up to band 5 and be pretty challenging. So we'll definitely see when we get there. For the second part, we've got the bacteria continues to grow according to this formula. So we've got N for number of bacteria is equal to 100 times 1.14 to the power of T. This is similar to the equation that we just graphed in the previous question. N is bacteria, T is hours. What is the number of bacteria after 15 hours? We have a table of values. They've already filled out 3 sections of it for us. They want us to figure out the 4th section to get 1 mark. So the question is, what are we going to do with this 15? Well, the 15 is a value of T. So we're going to put it into this equation. We're going to do 100 multiplied by 1.14 to the power of 15. That's going to give us N, which is the answer we're looking for in this question mark space right here. All right, so N is equal to 100 bracket 1.14 to the power of 15. Put that through the Casio and we get about 714. Because they've rounded their answers to the nearest number, I'm going to do the same thing. So the value of the question mark is 714 for 1 mark. Okay, part 3 for 4 marks. This is pretty challenging. We've got user values from N from T equals 0 to T equals 15. So it's basically saying, using this table of values, sketch a graph of this equation, use about a half page for your graph, and mark a scale on each axis. So the part that makes this question really challenging, which they don't really do in modern HSC papers, is they ask you to graph an equation, but they didn't give you an axis to use because back in 2004, you weren't answering in writing booklets like we are now. So rest assured that 9 times out of 10 for your HSC exam, if they ask you to sketch something, they're going to give you an axis because we don't trust you to draw your own because that's probably the hardest part. All right, which is why this is a 4-mark question. It should only be probably maybe 2 marks. So in your booklet, I have given you the axis to use, which looks like this. So all you've got to do is plot on these 4 sets of coordinates given to you in the question. And we've got the 714 that we figured out in part 2. So we're going to put on 0, 100, 5, 193. These are going to be your horizontal axis, normally your x-axis numbers. These 4 numbers are going to be the y-axis. Now it's going to be tricky to do this super accurately. So again, we're curve sketching, so we're just going to do close enough's good enough. If yours looks something like this, you're doing really well because this is pretty exact. So there is our 5 points plotted on. We join them up and we put an arrow on the end and we've got our exponential curve. You can ignore the dotted line for now. That's for the next part of the question. But the line there is the curve that we're looking for. Bacteria on the n-axis and time on the t-axis. Okay, and now to finish off, where it says using your graph or otherwise, estimate the time in hours for the number of bacteria to reach 300. Now, if you've done a good sketch for part 3, it makes this question really easy. If you've done a crappy sketch for part 3, it makes part 4 really hard. So we're trying to see the time corresponding to a bacteria of 300. So bacteria was the, let's have a look again. Bacteria was the vertical axis. We're trying to find the time. So we start with 300 for our bacteria. We see where 300 hits our curve that we just drew. Line it up down there. Because I've done mine pretty accurately, I can see mine is about 8.4. And like I mentioned last lesson, the HSC would accept a range of values, probably from low 8s to mid 8s. So if you said anything from 8 to maybe 8.2 to 8.6, you would more than likely be getting the mark for this question. So it doesn't have to be exact, it just needs to be close enough based on your sketch, which needs to be pretty decently. All right, so my answer is 8.4. Again, if yours is around that, close enough is good enough, and you've got your mark. All right, that is going to do it for today's lesson. There's some more practice for you guys to do in exercise 8A. There's a few selected questions that I recommend. All right, that's it. I'll catch you guys in the next video. Thanks so much for watching. See you later.